So part of the coolness factor of this morning, I think, in terms of the run of ideas, starting with Chris and Valerio, is our next guest, Andy. Let me call you Andy.
You certainly can.
We met in Seattle recently, and I'm now on his advisory board. We met through a pattern recognition maven who we know in common. And Andy is in charge of a project called the DIRAC Institute at University of Washington, which itself is tied into the construction and data flow which comes off of the LSST telescope, which itself has a camera built into it, all of which are kind of record-breaking events in their own way. So I thought we would start. So this has a position in this flow of conversations that will lead up to the CTO challenge. And it also has an amazing story of its own, which just stands up on its own. So we kind of have two jobs to do here. Would you share with the audience what is the LSST, maybe, and then go from there?
Yeah, so I'll talk a little bit about the project that we're doing, the Large Synoptic Survey Telescope, or the LSST, and then I'll try and put it in the context of some of the other talks that we've heard, both with Lee Hood last night, with Larry Smarr, and with Brian Jones on the retina. Normally as an astronomer, I get to sit here and say, we have the most data, we're covering the whole universe, and now I realize there's 10 to the, 1,437 different topological configurations just for the retina, and so I feel a little bit humbled sitting here. I guess we'll have to assume that all retinas are now part of the universe, and therefore we actually get the maximal amount of data again. So the project we're actually building, and I'll show you a picture of it. Oops, can we go back? So this is the LSST. It's a telescope that we're building in northern Chile. It's about an hour's flight north of Santiago, and then about 3 hours on a dirt road up into the mountains to see the
very
telescope.
High elevation.
Actually, for this telescope, most of the telescopes in Chile are around 1,400 feet. This one's only at about 14,000 feet. This one's only at about 7,000 feet, so it's actually fairly low down.
It's lower than we are here.
Yeah, but the good thing about it is it's dry, and the image quality is wonderful, so you get really sharp images when you take these pictures. What makes it the biggest observatory in the universe, in the world today, is not the size of the telescope, in fact. I mean, today we're building telescopes that are 30 to 40 meters in terms of the size of the mirror. That means the mirror would fit basically in this room. And those sorts of telescopes look at very detailed measurements of very distant objects. So they can measure stars as they move around black holes to measure general relativity, or look at distortions of galaxies to measure the mass of the universe. What's different about this telescope is it covers a very large area. So one picture covers about 3.5 degrees. And the reason for that is, and what drove us to build the LSST was, and this really goes back to what Lee Hood was saying last night, if you knew what measurement you wanted to make, if you knew the assay that you wanted or the medical test, you just do that, and then that would tell you whether there's some disease onset. But we don't, because we live in this complex universe, and we don't know what are the important aspects. So many of the reason that we take these large data sets is like creating a census of the universe, is so that we can actually begin to understand what these correlations are and how they relate to the physics of how the universe formed. Right. And I think that ties a lot to the visualization and the pictorial aspect of it, that a lot of what we're trying to do is to take big complex systems and come up with a simple compressed view that captures the information that we're interested in.
When this idea first blossomed with Larry Smarr and myself, it was about a year ago, or maybe more, 2 years ago. We're talking about the old style of astronomy where they would take a film and take another film, and then they would do this or have a stereopticon, or and see the change by holding it up to a light bulb.
But we talk about big data a lot, and astronomy's really been a big data field for 30 years or so. Those photographic plates were about 3 feet across, and the way we digitized them was someone, usually a graduate student, would look at the plate with an eyepiece and scan across it. And you could see the numbers of objects that they detected would correlate with the time since they last had a cup of coffee, or the last break that they had. And so to kind of get rid of those effects, we began to scan them with lasers. And now today we use CCDs. And excuse me, the important aspect about the CCDs is not just the amount
devices.
charge-coupled devices. Yeah, so the same technology you have in terms of the silicon in a digital camera that you may buy, a digital SLR, or possibly one of the CMOS cameras that you have on your cell phone. So similar in terms of silicon detecting light. And the nice thing about the LSST is the scale of this camera. So and you can do this tonight, and it's a great place to do this, is to go outside and look at Orion. And if you looked at Orion and you zoomed in on Orion's belt, and you can see the 3 stars on Orion's belt shown here on this view, these 3 stars are called the 3 sisters or the 3 kings. So one image from the LSST is about 3.2 billion pixels. So it covers about 3.5 degrees on the sky. And this is the only way that we can really begin to create this sense, is by mapping out the distribution of objects on the sky. And really the question we try to answer with the LSST is, what if you could observe the whole sky? What if you could detect everything that's moving and changing? What if you could record that digitally and then serve that to the community? And this means astronomers, it means scientists, it means computer scientists and statisticians, and it also means the general public. So what if you could do that, and then you could do that again and again and again over 10 years to see the time evolution of our universe?
So how often are you shooting the whole sky?
So with this camera, we can cover half the sky that's visible, so the sky that's visible from Chile, every 3 nights.
Every 3 nights. Yeah. And compare that to the last telescope that was trying to do this kind of survey.
Sure. So the last telescope, which is really where I started out, which was this project called the Sloan Digital Sky Survey, which was when I was a new postdoc at Johns Hopkins University. It took us 8 years to cover a quarter of the sky.
8 years for a quarter of the sky.
And so
You're doing the whole sky every 3 days.
Yeah. So it's about a 1,000-fold increase in data.
Wow. And the pipe that's coming off that telescope is carrying how much information per makeup a number? Per
So
day or per hour?
every night we produce about 30 terabytes of data per night, which isn't actually a lot when you think about it in terms of today's data. But we have to, per night, but we have to process this within 60 seconds, because what we're looking for is anything that's moved or changed. And there's about 10 million objects on the night sky that will move or change in a night. And so we have this stream of 10 million events that are coming out continuously every night. So a way of thinking, and then the real challenge, and where I think the real question that we have to address, and it comes back to some of these systems questions. We have a system where we want to go from collecting the data to processing the data to extracting the knowledge. And we understand how to do 2 of those. And it's extracting the knowledge that's the real challenge. Because if you imagine that you had, say you had 10 million events a night, so every 40 seconds you get another 10,000 events. So if you got 10,000 TV channels, and you had to select which one you wanted to observe, because to follow up those 10 million events, we really only have enough compute and glass or telescopes to follow up maybe 100 of those. So you have 10,000. You have to choose the one that you're interested in. We all know there's nothing on TV, so it's actually an easy choice. But then 40 seconds later, you have another 10,000. And then 40 seconds, you have another 10,000. You have to choose, do I stay on this object? Is this the object that corresponds to a gravity wave detection?
So we call it data triage.
Yeah. So filtering and AI and machine learning techniques to triage what you want to get out in order to follow it up. Yeah, it's a big area of research at the moment.
And you're using pattern recognition, or you probably plan to identify which of those are important or interesting.
Yes, so deep learning is becoming interesting for us. Yeah. Taking this stream and just filtering as it comes up. There's about 400 gigabytes of data per night just in that stream. And so we have to, with those 10 million objects, and so applying machine learning techniques to that is an area that really, that's where DIRAC is coming in. It's what we're trying to do, is to build these tools and make them publicly available.
Yeah. So if we just kind of connect with Brian Jones for a minute on this, right? He said, which we'll now try to refute, that the camera is not really the retina, but in fact, you're working to get toward that goal. Isn't that true?
Yes. So I'll just skip over a couple of slides. This is our camera. It's $187 million to build this camera. It's a little bit more expensive than your digital SLR, but it does have 3.2 billion pixels in it. So, as Brian said, you can't really take the Retina as a camera or even a video camera, but if you just think about the resolution that you can see on the sky, in this room, and you think about the amount of the room that you can see, then you can say that the Retina has equivalent of, say, 300 to 500 million pixels. So those 300 to 500 million pixels are then within a couple of inches on the back of your eye. This camera here is about 5 feet across. It's actually made up of not just one camera, it's 21 individual cameras. So it's 189 charge-coupled devices that can be read out can be read out in 2 seconds, and we take images that last about 30 seconds. So what's different from us in terms of the Retina is we can integrate for a large amount of time. So if you went outside and well, let me show you a picture of the sky. This shows you an image of the depth of the data that we will take with the LSST. The size of that region on the sky is, if you go to your eye test, right, and you go to these eye charts, and you look at the line that's 2020, the size of those letters, the size of this image is half the size of those letters. Right? So it's about 2 arc minutes on the sky. And there's thousands of galaxies within that image. And the nearest galaxy that you see, that big, beautiful spiral galaxy, is maybe 1 billion light years away. The most distant object is maybe 12 to 13 billion light years away.
Right.
So there's this huge dynamic range.
Right.
If you went outside and you looked up at the sky and you just sat there and you didn't blink, your eye would actually receive a photon from that most distant galaxy, but it would receive it once every 5 nights. Right? So what makes this different for us is that we have a big telescope that collects all the light, and also that we can integrate for large amounts of time. So this is about an hour's worth of integration on one point on the sky. And I'll just run this forward while we can talk about other things, just to give you a sense of the size of this relative to the scale of our, so this is about the size of the full moon.
Yeah.
And then this is, when we get, you'll see a little green shape, and that corresponds to the size of a single footprint of the LSST. And now you can begin to see you've got Leo above, and you've got Hydra below in terms of the constellations. And that gives you a sense of the single pointing of this telescope and how much data. We'll cover half of the sky with this telescope.
Wow. So this, again, to hark back, all these photons are coming in, just like with the eye.
Mm-hmm.
And you've got this camera plate, 26, and something has to happen there to help do the pre-processing to make the data stream usable at the other end.
Yes.
And how far along are you in that process?
So we have developed a lot of the infrastructure and the software and the algorithms to process this data. So the data is 15 terabytes, or 30 terabytes a night. One image takes about 1 second to transfer it from Chile up to the National Supercomputing Center, NCSA, in Illinois. And then we have 60 seconds to process that image. Before it actually goes up to NCSA, we do some small amount of pre-processing using FPGAs, similar to what the Retina does before it sends the signals out. Once the data gets to Illinois,
So the FPGAs are in Chile?
The FPGAs are in Chile, yeah. And we have sufficient bandwidth. We have about a 200 gigabit network that allows us to transfer those data directly up to Illinois. So we don't have to process it directly at the telescope in order to stream out all of these events.
Okay.
And so once it gets to Illinois, we have to take an image. We have to take an image that was taken, say, a week or a month before, and we have to subtract those two and see what's different. And then once we've
It
identified...
sounds like a difference engine, doesn't it?
It is exactly like a difference engine.
Okay.
It really thought about the Babbage connection as you were talking about it. And once we've done that, then we have to measure features. And so everything we're really doing is to try and compress this image into a different representation or a different visualization of the data that then gets streamed out to the community, and then they get to work with these features in order to say, this is interesting, this isn't interesting.
So it's a bit like what Chris and Valeria were talking about, where you either create a visualization of the data, in this case it's visual, or then you do an abstraction of that data before you disseminate it to the science community.
That's right, and understanding what is the right abstraction, I think, is the biggest challenge. It goes back to what I said at the beginning. If you knew what you were going to measure, you just measure it, and that would give you your answer. But we don't know what to measure, so we end up measuring many different things, and then how do you, what features do you measure, how do you abstract all of this information, and how do you display that to
And I assume that
scientists?
if I'm a really cool scientist, because they're the really cool scientists and they're the other guys, right? Then I give you a phone call and say, I'm very interested in that thing you just sent me. I want to interact with your system and go look at that in more detail. Is that how that happens, or how did that work?
So the data's public. So
Yeah, okay. Anyone
as
can-
a really cool scientist, you go and say, I'm really interested in that, and then you ring up your other friend who has another telescope, and you say, go and look at that object, because
okay.
I
So they'll
think that's a
focus-
new supernova or a hypernova or a gravity wave. Or,
Yeah, okay. It's probably worth, I think, helping the folks here in terms of why we're doing this, right? So let's step back for a minute. There's actually a reason why this whole project was created, aside from its power.
Right.
You want to explain the 3 drivers, or whatever the number you want to, 4 drivers?
In terms of the science
Yeah,
aspect?
yeah. What are
Sure.
you looking for yourself, or what was direct?
I'll tell you about 3 of them. I'll tell you 3 of them. I'll just briefly touch on 2, and then I'll show you some examples of the third one, which it's actually a little bit closer to home, and it might be more relevant both for the processing aspects and visualization, and also for the impact on society. So the 2 core drivers that we often talk about are cosmology, and in particular dark energy and dark matter. So why does our universe expand? Why does this expansion accelerate and not slow down? What is the dark matter that causes structures to form? And those are the kind of the 2 fundamental questions in physics today.
Yeah, I think that's worth underlining.
Right.
They really are probably the 2 most important questions in physics today.
Well,
Close to it.
Understanding those,
Yeah.
and the aspect is we don't have any theory behind it.
Yeah.
So the way you're going to understand them is through the data, and through accurate and high precision data, and lots of it. But the second aspect is that the potential to understand what dark energy may impact our understanding of fundamental physics, including gravity. It may be that you have to modify our understanding of gravity on large scales. And so these really are core physics, fundamental questions that we're trying to get
So have you ever heard of resonance theory?
I haven't heard of resonance theory.
I'm going to share it with you later.
That sounds good.
Okay, right.
I'll tell you the third one. The third one, which has a lot of pattern recognition, and it's much closer home. It's actually trying to understand our own solar system. Let me see if I can get this to display. There we go. This shows you a visualization of the positions of asteroids on the sky as a function of time. So what you're seeing here is a view of where the asteroids would be and how they move across the sky as they orbit around the sun. There's 1,000 times more asteroids than we can actually visualize here, because if you put too many on them, then you just don't get any real information or knowledge. It's hypnotizing, this image. It kind of flows backwards and forwards. Most of these asteroids are between Mars and Jupiter. If you can understand where these asteroids are, then you can understand the dynamics of where our planets were, because the planets move, and as they move, they can scatter asteroids. So you can use it to unravel the history of the universe.
Right.
What makes it a pattern recognition problem is you can see it's effectively like playing connect the dots, right? Each night you see where it is, and you have to connect those dots. But it's a million connect the dots all sitting on top of one another. And so that makes it a real computational nightmare, but fascinating. The little dots that you see at the bottom were these ones that were moving quite quickly. These were near-Earth asteroids. And I'll show you why the near-Earth asteroids are quite interesting.
Oh, we're in Russia?
Yeah. This is Siberia, this is Chelyabinsk, and this is February 2013. So that asteroid that burnt up over Chelyabinsk, it burned up at about 29 kilometers. It was it was only about 20 meters in size, and yet it had the energy associated with about 20 times the energy of the Hiroshima bombs. What was lucky about this asteroid was that it came in at a very shallow angle, so it had the opportunity to burn up. If it had came in a more direct angle, then it may have actually made it much closer before it did an airburst. And an example of that was a Tunguska asteroid that hit in, 1908, and it wiped out about 1,000 square miles of Siberian forest. Yeah. Living in Siberia seems to be quite a risky proposition. We all think about the asteroids and the asteroid that wiped out the dinosaurs, and they're about 1 kilometer in size, but we know where they are. We know about 90% of those kilometer-sized asteroids. Asteroids that impact the Earth at the scale of 20 to 50 meters, it happens every 50 years or so. And we don't have the opportunity, well, we don't know where they are. We know maybe where a few percent of these are. Mm-hmm. And we don't even know how many of these asteroids are. If you knew where they are, you can actually deflect them, and you can stop them. You can actually determine where they'll impact on the Earth or whether they'll impact on the Earth. And this kind of brings up the real challenge from the computational perspective. So if you look on the left-hand side, you can see in the top, from the top right moving across, you can see an asteroid. And it's hard to see, and that shows you why it's a real challenge. On the right-hand side, what happens if I move the telescope at the same speed as the asteroid? Now you can see the asteroid is fixed in the center. Mm-hmm. It's much easier to see. It's actually much brighter this way. So imagine that you don't move the telescope, but you move the data around. If you could do that, the data that we're taking with the LSST is sensitive to, just by finding an asteroid and watching how it moves, we can find objects down to about 150 meters. If you could do this sort of project where you could digitally move the images to find the asteroids without knowing where they are to begin with, I mean, it's a huge computational project. You could get down to asteroids that are on the order of about 40 meters in size.
What does that blow up?
What does that mean in terms of?
Blowing things up.
So a 40-meter asteroid would take out a major city.
Right, no problem.
And they hit, as I said, maybe every 30 to 50 years. So it's not an unreasonable thing to say that we should try and detect them early enough that we can actually deflect them. But it's a huge computational challenge. It's billions of searches for every single pixel in that image. And if you had infinite compute resources and smart algorithms, you could do that. Yeah. So the reason I'm saying that, there's a huge amount of data and there's a lot of science that we can get out. Yeah. But by thinking about it differently, by having different ways of actually processing the data, it increases the range of the science that you can get out by an order of magnitude.
So if we could do what we're talking about this morning, or what they're going to be talking about this afternoon, and operate on all this data way up here, mm-hmm. and do all that filtering and thinking and processing up here, and only drop down when we have to drop down, right?
Yeah.
That's the answer, right?
Yeah, so if you could filter out all of the objects that don't move, then you're just left with the moving sources. Right. If you can digitally stack all of these images and say which directions might have an asteroid and start pruning those out. Yeah. It's like a hierarchical view of information.
We do a visualization of the pictures, right?
Exactly.
And then we use that to show which things have the highest information content for what we're looking for. And we abstract that into some kind of a designed final result. And that's easy to ship to everybody. You can do a lot of operations on that.
Yes, and then you can see that it's extremely visual. Yeah. And so it's this hierarchy of science, hierarchy of visualization, and the filtering and the triaging of where real information actually is.
You seem to me like the ultimate, you meaning DIRAC Institute, seems like the ultimate customer for this project that we're going to launch this afternoon.
I think that the science communities themselves, I mean, us, yes, DIRAC, we're very interested in this sort of work. It's really the science community, because we talked about the system, right? The system, we know how to process data, we know how to store it, we know how to distribute it to the community. But when the community gets 10 million events, hundreds of gigabytes every night, it's not ready to actually do the science. And so I think it's the real science community, and I don't really actually just mean astronomy. I think it's true in oceanography, it's true in neuroscience, that all of this data is coming out, and it's how do you make it so a scientist, how can a scientist actually prune through these data, filter the data to actually look for the information? Yeah. And I think that's what's exciting about this pictorial processing.
And then you'd save the world at the end.
It's just a bonus.
We have Here we go. There's Chris, yeah.
So a couple of questions that are related. Are you going to be able to use this telescope to find the new Planet 9 that's supposedly lurking out there? And if you do, what will you name it?
So I've thought about both of those things. The first one is the telescope comes online in about 2 years, so it's probably going to be Planet 10 or Planet 11, because I think that Mike Brown has been taking observations in the last week, and it will be interesting to see whether he actually finds the planet. So I think he's in the best place to get it. But I do think we can map out the solar system out to 4 or 5 times the distance of Neptune, where we're currently looking. And that's really exciting. If we did find it, I'd call it Nancy, because that's my wife's name. And the amount of travel that I do, I think it's the only way that I could actually stay at home if I managed to do that.
Daniel?
Just a brief question regarding asteroids and impact. And the impact of having a computational system. You said 40 meters wipes out a city. What does 120 meters wipe out?
It roughly goes as,
Cube?
yeah, roughly the cube of the mass. It's the energy associated with. So the energy is mass times velocity
mv
squared.
Yeah.
And the mass just goes as the cube of the size. So that's a way of kind of doing a very rough scaling of the energy. It actually depends a lot
So
on what
40,
the
120
asteroid is made up of.
Yeah, yeah,
Yeah.
yeah.
Yeah, I work with the B612 and planetary resources, and it turns out actually that scary airbursts happen every 3 or 4 years, and that there were several that almost triggered DEFCON or even war. And so all sky awareness is one of the exciting things about your project. I believe that we should be getting it also in amateur ways by distributing much lower power systems that can then feed into the internet to 5,000 backyard amateurs or 50,000 backyard amateurs. But you're at the top end of this, and so the vast amounts of data that you are feeding in is not all sky awareness all the time, but pretty much all sky twice a week. Well, that's pretty darn impressive, and it really has. Speaking as a descendant of cavemen, I like being aware of everything that's going around me in all directions at all times. My retina wants to look look around in all directions. Comment, please.
I think that's a great comment. We work with the B612 organization. In fact, we have a couple of postdocs who are funded by B612 at the moment. I agree. I mean, my view is, in terms of just purely the asteroid and the science, there's an enormous amount of science that will come out of the LSST. It's a risk in terms of the impact. We're capable of finding these objects, and we should do that because we have the technology to be able to do that, and we have the intellectual ability to do this. And this is a project that we really should do. Yes, we need, I do think it ties into a lot of the amateur astronomers who, once you've found an object, can then go and say, where's it going to be, and refine the orbit as a function of time. And so it really could be an enormous community effort. Yeah.
We are out of time, and I want to thank you for scaring us and giving us great hope that we could actually find these things.
Thanks a lot, Mark.